Hello students, your physics teacher Hassan Darwish with you. In this video, I will make a direct application on how to calculate the period of oscillation of a compound pendulum. Now in this example, we have a device called metronome. It consists of a massless rod AB, this is AB, oscillating around the horizontal axis O, here it is, and carry at a distance d away from the axis a fixed particle m. Suppose here is a particle m. A tiny cursor of mass m along OB. Here the cursor slides along OB. Let OC equal x. Now write in terms of m, d, g, and x the proper period of small oscillations. Remember, small oscillations means we have simple harmonic motion, because we can in this case approximate sine theta with theta in radian. Okay, so let's start. Now you know that the proper period part A, the proper period of oscillation of a compound pendulum for a small amplitude is t0 equal to pi square root of I, which is the moment of inertia of the pendulum with respect to the axis delta, over m, which is the mass of the pendulum. Let me call it mt, representing the mass of the pendulum, g over a, where a represents the position of the center of mass of the compound pendulum relative to the axis of oscillation. So we find each term alone. I, which is the moment of inertia of my pendulum, is equal I of the rod, I rod, plus I of the particle at point A, plus I of the particle at point C. Okay? See here. Now, massless rod means the moment of inertia of the rod AB is 0. Here is m at point A, and here is m, small m, at point C. So this is equal to 0 plus m d squared plus m x squared. You know, the moment of inertia of a particle with respect to delta is mr squared. You remember the rule. Now, mass of the pendulum, mp, is the mass of the particle at point A plus mass of the particle at point C. Now we are left with A, which represents the position of G relative to delta, which is, we have the mass m at point A, distance d, minus mx, because this is m1, x1 for example, plus m2, x2 over the total mass of the pendulum, which is m plus m. Why there is minus here? Go back to the figure. Here it is. We've chosen, and this is always the case, x prime x, x prime x downward. Now here is the origin of x prime x. Okay, so this m is in the negative side at x, and this is in the positive side at d. Okay, now let's replace here in the period. So the proper period or natural period of our compound pendulum is 2 pi square root of I, which is m d squared plus mx squared over m plus m, the total mass, gravity, multiplied by A, which is md minus mx over the total mass. Now we simplify this expression. We may cancel m plus m with m plus m. We get 2 pi square root md squared plus mx squared over g into md minus mx. This is the expression of our compound pendulum. Notice here, this expression is a function of x, you see? And because our slider here our cursor may slide along OB, means x is variable in general. We can change x. If we vary x, then the period of oscillation varies. Okay? Now part 2, or part B, determine the value of x. So where should you place this cursor? Determine the value of x so that the period is infinitely large. Interpret the result physically. Okay. So here part B, x equal how much so that t0 tends to infinity, infinitely large. We notice that this proper or natural period is a function, as I said before, is a function of x, which has the form 2 pi, radical m d squared plus mx squared over g, which is a constant, into md minus mx. Okay. You know from mathematics, t0 tends to infinity when the denominator of the function is 0, right? Because this numerator is always positive. So when md minus mx tends to 0, is that true? This means that x tends to, wait a minute, x tends to md over m, right? So in this case, if x equal this value, means if we have the values for m, d, and m, then the period becomes infinity. What does this mean? Let me replace here x in this expression for g. Let me replace here. In this case, we have A, which is OG, is equal m d minus mx over the total mass of the pendulum. In this case, equal to 0, okay, or tends to 0. What does this mean? It means that the axis delta, which was at point O, now passes where? Passes in the center of mass of the pendulum. But you know that in this case, In this case, if the axis passing through G, the sum of moment with respect to delta, which is represent in this case the moment of the weight of the pendulum, weight of the pendulum, equal moment of the reaction of the axis delta equal to 0, since in this case W and R intersect delta. Since in this case W and R intersect delta, okay? So, and already we have sum of forces equal to 0. So what do you obtain when the sum of moment equal to 0 and sum of forces equal to 0? We obtain what? Equilibrium of the rigid body, which is the pendulum here. So we get equilibrium. Okay? In reality, no oscillation. In reality, no oscillations. Okay? That's enough for this video. In the next video, I will explain the simple pendulum. Okay, take care. Bye-bye.